In this video, we're going to look at what we call line spectra and how that relates to the electron's structure around an atom. When gases are excited, in other words, when they are given energy, the electrons in those gases then have more energy than normal. As electrons go back and forth from higher to lower energies, light is emitted. And again, what we're going to investigate is how that relates back to electron structure. What we see here is an illustration of what we call line spectra. Here we have gases in this tube which are being hit with electricity, which excites those gases and causes them to emit light. When we then look at that light through a prism, what we see is that only a few colors show up. We don't see all the colors of the rainbow like we would see with just sunlight through a prism, for instance. Down here, we see what we would observe if all light, for instance sunlight, is passed through a prism. We see all the colors of a rainbow, and this is in fact what does cause a rainbow. Water acting as a prism and separating the various wavelengths of light, which we observe as different colors. However, we don't see the same thing if we are looking at excited gases through a prism. And so here we have a gas tube that contains hydrogen. We excite that hydrogen with electricity, pass that light through a prism, and what we end up seeing, in fact, are only 4 wavelengths of light. We have violet light at 410 nanometers, a blue light, which you may or may not be able to see on your screen. We have a greenish light at 486 nanometers, and then red light at 656 nanometers. And those are the only 4 colors and wavelengths that we see. It turns out that the wavelengths of light which are emitted are unique to each individual element. And here we see just some more examples of those overlaid on each other. We have the spectra of hydrogen, mercury, and neon. And we know that they are quite different from each other. And so the question that we have to now ask ourselves is why? Why do different elements emit different wavelengths of light when they're excited? The answer to that question is something that Niels Bohr figured out, in that it lies in how electrons are arranged around a nucleus. Bohr asserted that these line spectra indicates that electrons are not just randomly located around a nucleus, but instead are confined to different what we would call orbits. And so we could find electrons here on one orbit, or here on another, or out here on another. But that we would not, in fact, find them at various other spots. So we would not find electrons where I've drawn them there. We would only find them on these specific orbits instead. And so we start to number these orbits. We have what we call n equals 1 here at the first orbit, n equals 2, n equals 3, and so on. But the big takeaway from Bohr, again, is that electrons can only be found at these certain orbits, at these certain levels. You will not find them in other locations. And that, in fact, what's happening is that as electrons are excited, they might move to a further out orbit and then come back in. And so, for instance, we might have an electron here on n equals 1, and if we hit that electron with energy, it might give it enough energy to jump out here to n equals 2. That electron will almost immediately fall back down to n equals 1 again. As it does so, it's going to release the energy that it had absorbed. Now let's think back to what we know about relationships between energy and wavelength. You'll recall that we were able to relate energy to frequency and also relate energy to wavelength. What this means for us, What this means for us is that certain energies, as they are released, will express themselves as wavelengths of light. And so as this energy is being released when this electron drops back down to n equals 1, in this case we see that as a red light, illustrated here, corresponding to the wavelength of red light. Similarly, if we have maybe another electron here at n equals 1, and we give it enough energy to come out to n equals 3, it will almost immediately fall back down to n equals 1, and when doing so, will release energy corresponding to a particular wavelength. And so it's these different transitions which result in us seeing different colors in those line spectra. The different colors correspond to different jumps or different transitions between these energy levels. And so this led to a new view of the atom. Previous to this, it was thought that electrons could pretty much exist anywhere and existed in random locations outside of the nucleus. Bohr now introduced this new theory, which was eventually called quantum or wave mechanics, that electrons can only exist in these very discrete orbits, and electrons are restricted to these different energy states, these different orbits around the nucleus. And this is just another way to illustrate that. We could have an electron here on what we call the ground state, and if we give it enough energy, it might be able to jump up to n equals 2, to our second orbit, but then again, it will almost immediately fall back down to the ground state, releasing that energy. Or we might have an electron that's already here at n equals 2. Supply it with enough energy to jump up to n equals 5, at which point it would almost immediately drop back down to n equals 2, releasing a certain amount of energy. And so this type of diagram just gives us another way to illustrate these transitions that we've been talking about. To look at some of the terminology, the ground state is going to be our lowest energy level. In this case, we're talking about one electron systems, and so our lowest energy is going to be here at n equals 1. An excited state is going to be at any energy level higher than the ground state. And so in these one electron systems, we would be talking about any energy level beyond the first. The Balmer equation provides for us a mathematical relationship among these observed frequencies and wavelengths. An equation was found that could actually calculate the wavelength of the red, green, and blue lines in this visible emission spectrum of hydrogen from the various transitions. And so again, just to sort of recap what we're talking about here, we've got an electron that is here at our ground state at n equals 1. It absorbs enough energy, in this case 984 kilojoules, to send it up to an excited state, and almost immediately drops back down to the ground state, releasing that energy that it had taken in. And the Balmer equation gives us a way to calculate that wavelength of that energy release. So in the Balmer equation, the inverse of the wavelength, 1 over the wavelength, will equal R, which is the Rydberg constant, which we'll see in just a minute, multiplied by 1 over 2 squared minus 1 over n squared, where in this case 2 is going to represent our ground state, our second orbital, and n is anything greater than 2. N would be any sort of excited state. And so what the Balmer equation allows us to do, again, is to calculate the actual wavelength of these various transitions. So we have our Rydberg constant here, so R will be equal to 1.0974 times 10 to the 7th inverse meters. And what we can do is to actually calculate the wavelength released for each of these transitions. From 6 back down to 2, 5 back down to 2, and so on. And so we can calculate the wavelength of these various transitions using our Balmer equation, which tells us what color they would be. And so let's look at an example of that. Here we're going to calculate the wavelength from the transition of 6 back down to 2. And so 1 over our wavelength is going to equal our Rydberg constant, times 1 over 2 squared minus 1 over 6 squared. And so we do out the math of that, and we get our inverse wavelength, 1 over wavelength, equal to this number. And so then our wavelength is going to be 1 over that, or 4.1 times 10 to the negative 7th meters, which is equal to 410 nanometers, which is approximately the wavelength of blue light. So this tells us that a transition of an electron that started at level 2 and then was given energy to raise up to an excited state at level 6, when it drops back down to 2, will release light, which we will perceive as blue. And that's in fact what we see here. So we were talking about using the Balmer equation here. And so the Balmer series is that entire series of the hydrogen spectrum. 6 down to 2 gives us 410 for a blue light. 5 down to 2 gives us 434 nanometers, which is a bit of a violet light. 4 down to 2 gives us 486 nanometers, which is our green light. 3 down to 2 gives us 656 nanometers for a red light. Two other important series are the Lyman series, which are transitions of 7, 6, 5, 4, 3, and 2, all down to 1. We are not able to visually see those because the wavelengths that those give off are in the ultraviolet portion of the spectrum. Likewise, we have the Ritz-Passon series, which are transitions from 7, 6, 5, and 4 down to 3. But again, we're not able to see those as the wavelengths emitted are in the infrared series. So the Balmer series is the only transitions that give us visible light. Now let's just recap real quick and remember what we're actually looking at here. In this very crude rendition of an atom, we have our nucleus here in the middle, and then our various what we call Bohr shells, n equals 1, n equals 2, n equals 3, and so on. And so if we have an electron that's here on our second energy level, that's given enough energy to come out to the fourth energy level, that almost immediately drops back down to the second, and in doing so releases energy. And in this case, it's energy associated with, for the fourth down to the second. And so we would actually visualize that transition as green light at 486 nanometers. And so, to recap, what things like the Bohr model and the Balmer series allow us to do is to describe the line spectra that we see of the hydrogen atom. The big limitation of this model is it does only work for one electron systems, such as hydrogen or helium+. Bohr did win the 1929 Nobel Prize for this work, however, because it really gave us a lot of insight into the nature of electrons and allowed us to see that electrons are arranged around the nucleus in these various shells. And so we have here a depiction of those first 5 shells. Our nucleus in the middle, and then the first 5 shells where electrons would reside. And so the big takeaway from this video is this slide here, that electrons will exist on these Bohr shells. They will not exist in random locations outside the nucleus. They must be located on these various shells. I hope this video has been helpful in visualizing electron structure, and be sure to come see me if you need some extra help.